Hi class, this is Sir Alex Basco and welcome to our lesson in General Biology 2. Today we are finishing our discussion in lesson 7 and we are going to talk about metabolic rates. It's basically a topic on how animals uses energy in order for them to survive. We've discussed a long time ago about cellular respiration. We know that in order for us to survive, we need to partake food, and then we have to convert that food, break it down to get the molecules that we need, more specifically glucose, and then we take that glucose inside the cell and inside the mitochondria, wherein we undergo the process of cellular respiration to create ATPs, which then the ATPs is used for our body in order for us to survive. This whole process of partaking in food, breaking down the food, turning the glucose into or transferring the glucose inside the cell into the mitochondria and transforming it into an ATP is actually whole part of the metabolic process, and that process is actually called bioenergetics. Bioenergetics is basically the flow of energy through an animal, and bioenergetics actually determines how much food an animal needs, and it is affected by the animal size, activity, and environment. So this is the whole process that I was talking about earlier. In the whole process of bioenergetics, animals can either be an autotroph or an heterotroph. We've discussed about this. Autotrophs, from the term itself, autotrophs, they create their own food. While heterotrophs, like humans ourselves, are animals that needs to consume other products or other species in order for them to get the nutrients and get the food molecules, the organic food molecules they need in order to create ATPs. This whole process of bioenergetics actually has priority. The food molecules that we partake and use to create ATP is first, the ATPs that we create are first used in order for us to survive. So the main priority of our body is to survive. So all the cellular work that it needs in order for us to move, to blink, to breathe, those things, anything that our body needs in order for us to survive. The rest of the cellular respiration work, the other ATPs that is produced in other products, is then used for biosynthesis. So biosynthesis is the rest of the activity that our body needs, such as growing, storage in forms of in terms of fat storage in our body, and the reproduction. It means the creation of our reproduction or gametes. So you may think the reproduction of our gametes is, it's important for survival. Yes, it's important for the survival of our species, but not ourselves. And we cannot help the survival of our species if we do not survive first. So the first thing that the body does is actually, our body is very smart, is to use the cellular respiration, this whole bioenergetics, to create the energy we need in order for us to survive first. And then next, after everything that we need in order to survive has been satisfied, then the rest of the work is then transferred into the creation of in order for us to grow, in order for us to store energy through fat, and even the production of the gametes, the sex cells and the sperm cells. So those are just some examples of biosynthesis. However, do not think that this is just a step-by-step process, that I need to do this first and then this. Well, it may look like that. Basically, what is happening is it automatically segregate the work. So for example, you can think of this whole process as 100% work. What the body does, it immediately dedicates some of the work, a percentage of the work for survival, and then the rest for biosynthesis. So what is happening in reality, this is happening along at the same time. It's just the work is being separated. I hope that is making it clear. But again, what we have to do first is for us to survive, and then the rest follows. Another thing that is important though is that ATP production actually generates a lot of heat. This whole bioenergetics generate heat. From the moment that we partake our food and digest the food, as we break down the particles, we are producing heat. And then during the cellular respiration, it actually produces tons of heat as we do all break down the glucose into acetyl-CoA, etc., etc. And then as we do the electron transport chain, a lot of that produces heat. And then also as we use the ATPs, we again also produces heat. So us as humans, as an animal, part of the animal species of the earth, we are actually losing a lot of body heat. So it is important for us to maintain a certain body heat. That's why from our previous discussion, remember, humans have brown fat along their neck and along their shoulder that helps us create this heat if ever we are losing, we are not producing enough heat for our body. So we have to maintain that internal temperature. So I hope it's clear. That's what happens in bioenergetics. So the energy requirement for our survival is dependent on a lot of things such as size, activity, environment, and whether our survival is satisfied first, and then the rest biosynthesis. Next, let's talk about metabolic rates. Metabolic rate is basically the amount of energy a species or an animal needs per unit of time, and it is measured in terms of joules or calories. Metabolic rate is dependent on a lot of factors, such as the activity, the size of the person, the food that you take, and the environment that you are in. So just remember that metabolic rate is just the amount of energy that you use over a period of time. And there's different ways to measure metabolic rate. The first one is heat loss. Remember from just the like I mentioned earlier, everything that we do in bioenergetics produces heat. So if we measure the amount of heat that our body loses, we can actually stipulate or measure how much energy are we using in order for us to basically survive and exist in our everyday living conditions. Another way that we can measure metabolic rate is the amount of oxygen consumed. This is necessary. Why oxygen? Well, cellular respiration. Without oxygen, we cannot undergo cellular respiration. So we can also stipulate how much energy we use using the amount of oxygen we consume, or also we can use how much carbon dioxide we produce, because remember, the carbon dioxide we exhale is actually the byproduct of cellular respiration. I hope you guys remember that water and carbon dioxide are the byproduct of cellular respiration. And lastly, we can also use the food consumption. We can measure how much food we intake over a long period of time. For example, a gram of protein is actually equivalent to 4.5 kilocalories. So if you measure every single thing that you have eaten over a long period of time, you can actually use that as well to measure your metabolic rate. And then there's something that we call the minimal metabolic rate. Minimal metabolic rate is basically the smallest amount of energy that we need in order for us to survive. Depending on whether you're an endotherm or an ectotherm, as humans, we are endotherm. The metabolic rate, the minimal metabolic rate, is dependent, or it depends on whether you're an ectotherm or an endotherm. Again, this is a minimal metabolic rate. When we talk about minimal metabolic rate, again, this is the smallest amount of energy that you use when you are basically doing nothing, when you are at rest. So it means you are basically, you are not digesting food, you have a you are not sleep deprived, you are not stressed. Then you can use you can actually measure the minimal metabolic rate, or the smallest amount of energy you used to survive. So we call that actually the basal metabolic rate for endotherm. There's actually two not 2 units. There's actually two ways to measure our minimal metabolic rate. One is the basal metabolic rate, and the other one is called the RMR, or the resting metabolic rate. And actually, RMR is more accurate. Basal metabolic rate is very constricted. If you want to measure your basal metabolic rate, you would need to have first an 8 hour of sleep, and then you have been fasting for 12 hours. After you've done that and you are not under a lot of stress, then you can actually measure your basic metabolic rate. RMR, on the other hand, is just your metabolic rate after resting. It's much less constricted. So statistically, RMR is actually more accurate. But more interestingly, how do we actually measure that? How do we measure the amount of energy we need in order for us just to survive? There's actually an equation. The equation that I'm going to show you is the equation for RMR. I'm going to show you this because this is more accurate. It's usually 10 times your weight in kilograms plus, I believe it's 5 or 5.5, I'm not sure, but I think it's 5. 5 times your height in centimeter, and then minus 5. Oh, this should be I believe they're supposed to be 5, or this is 5.5, but this is close enough. So 5 times your age in years. And if you are a male, you have to add 5. If you're a female, you have to subtract 161. So using this equation, you can actually measure how much joules or kilocalories, how much energy you need in order for you to survive under a resting condition. And later, I will show you why this is very important. Why do we need to take this? The clue here is from the term itself, basal. This is the base. This is the smallest, or this is the foundation energy you need just to survive. Anything else that you do outside of this, outside of resting, or basically outside of existing, you're basically not doing anything during RMR, you're not talking, blah blah blah. The rest, then you actually take this RMR, this value, and then you multiply it at a certain values to identify these values is dependent on your lifestyle, no? And you can actually then identify how much energy you need in order for you to survive with that lifestyle that you have. So this is for endotherm. Ectotherms, on the other hand, has a different minimal metabolic rate. The minimal metabolic rate for an ectotherm is called an SMR, or standard metabolic rate. The reason that they are different is because ectotherms are dependent on the surrounding temperature. Their body temperature is dependent on the temperature of their surrounding. Therefore, the metabolic rate of an animal, specifically an ectoderm, changes depending on the temperature that they have. So you can measure their minimal metabolic rate or their standard metabolic rate under a specific temperature. Measuring the average BMR, or the average rate across all human species, we actually need about 1600 to 1800 kilocalories for male, and about 1300 to 1500 kilocalories for female. This is the average amount of energy a person needs in order to survive, or you can also think of this in order for you to maintain your weight. That's also another way to say it, to maintain your weight. So by taking this amount of food, this amount of energy in food, only 1600 or 1800 kilocalories as a male, will keep your weight as long as you are not doing anything, as long as you are at rest. But then again, this is just an estimation. Please do not get confused it as something that is very specific. Humans vary. We vary. We are different across a lot. We vary across a lot of things, no? So the average metabolic, or the average BMR of one person may not be the same as yours, because one, you are two different person, and also there are different things that affect metabolic rates. Number one is the size. So for example, you have your father, let's say, is much more bigger than you are. The size would actually affect your BMR. So if you actually see here, weight is a massive factor. You multiply it by 10. So if a person is much larger than you, or way much heavier than you, it means they need more energy in their, in just for them to survive at the resting rate. Okay, but one thing though is that size actually is has a lot of unanswered questions in the field of biogenetics or bioenergetics. We know so far that the larger the body is, the higher the metabolic rate. No, but interestingly, so first, so this has a uh, direct proportion. So they are directly proportional. So higher weight means higher metabolic rate. But if you actually look more closer and you measure the weight in terms of per kilogram, so you're not taking the whole weight itself, you are taking per kilogram, what we notice is that there is an inverse relationship. The higher, or basically what happens is that the smaller the animal is, the higher their metabolic rate. So what do we mean by that? Let's look at this two graphs right here. So the smaller the animal is in terms of weight, the lower their metabolic rate. But why is it that the smaller animal have higher metabolic rate per kilogram? Okay, so I want you to think of it this way. You have two animals. Animal A, let's say, is about 5 kilogram. Animal B, on the other hand, is 25 kilogram. Okay, so animal A, we know, since it is much more smaller in size, it has a metabolic rate of, let's say, 10 kilocalories per kilogram, which tells us that the metabolic rate of animal A is what is actually equal to 50 kilocalorie, or 50 joules, whatever units that you use. Now let's look at animal B. Animal B is much more larger. And larger animal, we know, should have higher metabolic rate. Therefore, it should have at least a higher metabolic rate than animal A. But why is it that it per kilogram it has a much lower metabolic rate? Well, as since it's a bigger animal, let's say this animal has a metabolic rate of 4 kilocalories per kilogram. If we measure this 25 times 4, what will tell you is that animal B has a metabolic rate of 100 kilocalories. The reason that the larger body, or that the larger animal has higher metabolic rate, if we take everything into account, is because just of their massive size. The fact that they are massive, that they have more per kilogram, gives them a higher metabolic rate. But if we look closer and closer, and if we look at them individually, 1 kilogram at a time, you would notice that smaller animals has a higher metabolic rate per kilogram. That is the difference. So you can see here, this animal has a higher metabolic rate per kilogram compared to the bigger animal. But if we look at them overall in their total weight, the smaller animal has still a smaller metabolic rate than the bigger animal. So this is how this makes it very confusing for a lot of biologists. How is this possible? One of the hypotheses is thinking that because the smaller animal is smaller in sizes, so the volume to the ratio of their body is much more bigger than of a bigger animal. So what they're trying to explain is that smaller animals tends to use more energy to keep themselves or to keep their body warm. So that's one of the hypotheses that a lot of scientists are thinking. But until this day, we have not answered the question: why is this true? Why size? Why we know that this is true, but we don't know the reason why this situation happens. Okay, so if we go back to our basal metabolic rate earlier, if you have two males and a male A is much bigger than male B, male A should have a bigger metabolic rate than male B. But one thing that the basal metabolic rate equation is not showing you is it is also dependent on the person, whether on their muscle mass, because muscle actually burns more calories than fat. So for example, if you had a male that is 160 kilogram, male A, and male B is also 160 kilogram, but let's say the muscle mass of male A is, let's say, 10 kilograms. So he only has a muscle mass of 10 kilogram, but male B has a muscle mass of, let's say, 80 kilograms. So his body is much more muscular than male B. Male, despite having the same sizes, the same weight, male B would actually have a higher metabolic rate for the simple reason that muscle actually burns more calories than fat does. No, so for those who are trying to lose weight, sometimes you may feel discouraged that you're not losing weight. Just the reason for that is because the fats that the body has is burning less than the person probably that is much more already muscular. So people that are already starts to be more muscular gains more muscle faster because they're using much more energy at a higher rate. So that's just something that is true across that is something that is actually true. So even though you have the same weight, it's the muscle mass also affects your metabolic rate. And lastly, also activity. So depende kung you are very active or you have a sedentary life, anything that is beyond the activity of BMR or SMR will consume energy. So this is like I mentioned earlier, why do we have to take BMR and SMR? Well, after taking BMR, so we usually have certain values. We multiply it at a certain value which is depending on the activity. Later. So here. So it's not that. So depending on the activity, for example, usually an activity that is very strenuous, for example, running really fast or having weightlifting, usually you take your BMR and you multiply it by either about 2 to 4, and that will give you your new BMR for that activity. This is the amount of energy that you're using to do that activity. So that's how we can measure how much BMR or how much energy is consumed by an activity. And the maximal metabolic rate is basically the rate at which the maximum ATP is usage. So this is a lot of activity that is happening. So this is where you're running fast, you're lifting weights, you have intense physical labor, all of which are using the maximum amount of ATP that your body can, then you will have your maximal metabolic rate. So if this activity right here, 2 to 4, is actually the multiplication for maximum activity. So if you take your BMR, you multiply it about, depending what activity you are, then that is the BMR for that activity. So average metabolic rate is about 2 to 4 times that BMR SMR for land animals. But if you actually have humans, if you look at the average metabolic rates of humans, you would notice that the average metabolic rate of a human, this is not their BMR. This is already them living, this is them already working, this is them already talking, having fun, etc., is only 1.5 of your BMR, which actually tells us that humans in developed countries has a much more sedentary lifestyle, meaning they move less, they have less activity overall than, for example, the animals on land, or even other humans from a much less developed country wherein they had much more physical labor. So halimbawa yung mga magsasaka natin, has higher average. If you take these farmers and measure their average BMR, they would have higher BMR than, for example, the people working in an office who has been sitting in their office for at least 8 hours a day. It's just for the fact that the farmers has higher activity, and it's their labor is much more strenuous than those who are in the office. Okay, so that is what affects your metabolic rate. Next, depending on the species, we actually budget the energy that we have annually. So this budgeting of energy annually, when we talk about energy budgeting, where does the species, or where does the animal use a certain amount of their total energy within a year to what activity? So dependent on what kind of animal you are, or whether where you are, your environment, behavior, size, and how you thermoregulate, it will actually affect how you would budget or where you would allocate your energy. So if we take these animals, for example, if you look at their first, I want you guys to look at their thermoregulation. A penguin spends less energy in thermoregulation. It's because penguins are actually very insulated. They have a lot of body mechanisms within them that keep themselves warm, that they have a lot of tools within their belt to keep themselves warm. But if you look at this deer mouse right here, the fact that it is much more smaller, remember, per kilogram, one of the hypotheses is they have to use more energy to keep themselves warm. And if you look at here, the energy that this mouse, or this deer mouse is using is much more greater. It's allocating more energy in warming its body. And then if you look at a for example, this right here, this boa, this python, you wouldn't see any energy for thermoregulation, because a boa is a reptile, and a reptile is an ectotherm. And ectotherms depends their body, they adjust their body depending on their environment. So they do not need to use energy to warm themselves up. They basically adjust their body kung ano yung temperature ng surrounding nila. But what you can see here is they spend a lot of time growing as well, or growth. They have growth activity, which this two does not have, because these animals right here, upon the arrival of being an adult, they already stop growing. This is an adult penguin and an adult mouse. But for a reptile, even though they're actually very old, or they're already an adult, they do not stop growing. Kaya may mga nakikita kayo na mga sawa or the snakes, boas that are really big. It's because they do not stop growing. So they spend a portion of their energy used to grow their body for growth. So again, depende sa environment mo, behavior, size, and thermoregulation affects your budgeting. And on the module, you would see more explanation on the percentages of, for example, a 40-year-old woman, on how that woman will budget their energy. So after knowing this, we can now actually learn about the three important concepts in bioenergetics. Number one, smaller animals has much greater energy demand per kilogram, meaning the smaller the animal is, if you measure the amount of energy that they use per kilogram, it is actually much more higher. It's not cost effective, it costs more. Ectoderms require less energy per kilogram than endotherm. So an ectoderm will require less energy than an endotherm. And lastly, size and energy strategies influences the total annual energy expenditure. Meaning, depende sa size mo and dun sa energy strategy mo, depending on your needs, such as are you a reptile that needs to grow all day long? Are you a small animal that needs to keep to warm itself? Or are you a penguin that already insulated, so you're using less time for warming yourself up and you just use much more of your energy for activity, because in order for you to get food you need to swim, you need to catch the fish in the ocean, etc. So depending on a lot of things, you would budget your energy differently. And lastly, it's not covered, animals can actually save energy via torpor. Torpor is basically the physiological state of an animal in which the activity and the metabolism of that animal decreases. We also know this, you're probably much more familiar from the term hibernation. Hibernation is winter torpor. This is when the animal's activity and their metabolism decreases during winter. And the most popular animal that we know that do hibernation is a bear. And the reason for that is because they have much less food during winter, so they have to save their energy, because it would actually take much more energy to keep their bodies warm. So during hibernation, what actually also happens is that the overall temperature of an animal decreases. Some animal actually in fact decreases their body temperature below zero, and they are in the state of constant freezing, but they are not totally freezing. So hindi sila nagyayelo, pero yung katawan nila is sobrang lamig. It's very intriguing. But yeah, hibernation is one of activity for the animal to save energy whenever they have to, in order for them to survive. And then there's also a summer torpor, and this is estivation. Probably not familiar with this, but some of the animals that do estivation is snails. During very hot season, snails conserve their energy by lowering their metabolism and lowering their activity. The reason na marami kayo nakikita na snail during rainy season is because they're coming out of their estivation. So during the summer, tago sila. They're trying to cool they are trying to cool themselves in their bodies by some actually bury themselves underneath the ground, because the temperature on the ground actually does not really change that much. No, it's very constant. So to cool themselves out, they bury themselves in the ground, and what happens is when the rainy season starts, it's not hot anymore, they come out of the ground, they come out of their estivation. So this is some of the few ways that animals conserve energy. Another thing is there are some animals that do daily torpor. For example, a bat. A bat undergo a torpor during the day because it's too hot, and so they save energy during the day. And then when the night comes out, the reason that we have so much bat is they come out of their daily torpor, so they are more active at night. And the opposite is true for hummingbirds. For hummingbirds, they are sleeping at night and they're very active in the morning. So this is some of the ways that animals save energy. So that is all for part 3 of lesson 7. This is the end of lesson 7. If you guys have any question, please do not hesitate to message. Thank you so much, guys, and may you guys have a great day.